Unleashing the power of direct memory access (DMA) controllers. In the bustling realm of computer architecture, optimizing data flow is paramount. The CPU, the central maestro, oversees everything from calculations to interactions with external devices. But when it comes to bulky data transfers, the CPU can become a bottleneck, akin to a single toll booth handling a highway full of trucks. This is where direct memory access (DMA) controllers come in, offering a dedicated express lane for high-speed data movement, allowing the CPU to focus on more critical tasks. The bottleneck blues. Why we need DMA? Imagine a single traffic controller managing every vehicle on a highway. This is similar to a system without DMA. The CPU, acting as the controller, handles both data processing and data transfer between itself and I/O devices like storage drives or network adapters. For small data exchanges, this setup works. However, when dealing with massive data volumes, like video editing or large file transfers, CPU involvement creates a bottleneck. Here's why. CPU burden. The CPU spends a significant amount of time managing data transfer specifics, limiting its ability to perform other tasks. Bus contention. Every data transfer requires access to the system bus, the highway connecting the CPU, memory, and I/O devices. Frequent CPU involvement in data movement leads to increased bus contention, slowing down overall system performance. The DMA controller. A dedicated express lane. A DMA controller acts as a specialized coprocessor, offloading data transfer duties from the CPU. Think of it as adding a dedicated express lane for high-speed data movement alongside the regular traffic flow managed by the CPU. Inside the DMA engine. A step-by-step look. The following steps illustrate a typical DMA transfer process. Configuration Central. The CPU prepares the DMA controller by providing details like source and destination. This specifies the location of the data to be transferred, which could be memory addresses or I/O device registers. Transfer size. The amount of data number of bytes or words to be moved is defined. Transfer direction. This indicates whether data is being read from the I/O device to memory read or vice versa write transfer mode. Some DMA controllers offer options like burst mode, where data is transferred in continuous chunks for improved efficiency. Requesting access. The I/O device initiates a DMA request when data is ready for transfer. This request could be triggered by various events, such as a completed disk read operation or a full network packet reception. Taking the wheel. The DMA controller signals the bus arbiter, a component that manages bus access for different devices. Upon receiving permission, the DMA controller takes temporary control of the system bus's address, data, and control. This essentially pauses regular CPU access to the bus for the duration of the transfer. Data on the move. The DMA controller takes over the data transfer process. It generates memory addresses in sequence based on the transfer size. It reads data from the I/O device or writes data to the I/O device using the system bus. It updates an internal byte counter to track the progress of the transfer. Job done. Once the transfer is complete, the DMA controller relinquishes control of the buses, allowing the CPU and other devices to resume normal operation. It then notifies the CPU with an interrupt, indicating the completion of the DMA transfer. The power of offloading. Benefits of DMA controllers. The advantages of utilizing DMA controllers are substantial. Performance boost. By offloading data transfer tasks, the CPU is freed up to focus on other computations, leading to a significant performance improvement. Speed demon. Dedicated hardware on the DMA controller allows for fast and efficient data movement compared to CPU-controlled transfers. Reduced CPU overhead. The CPU is only involved in initializing and finalizing the DMA transfer, minimizing its workload. Real-world applications. Where DMA shines. DMA controllers are prevalent in modern computer systems, playing a vital role in various data transfer scenarios. Disk data transfer. DMA is essential for efficiently reading and writing data to storage devices like hard disk drives and solid-state drives. Network adapter data transfer. Network adapters rely on DMA to move incoming and outgoing network packets between memory and the network interface. This ensures smooth data flow during network communication. Audio-video data transfer. Real-time audio and video streaming heavily utilizes DMA controllers for transferring large amounts of data between memory and sound cards or video capture cards. In conclusion, DMA controllers act as unsung heroes in the world of computer architecture. By offloading data transfer tasks, they significantly improve system performance and allow the CPU to focus on more critical operations. From enabling smooth test your understanding. Question. What is the main advantage of using a DMA controller? Answers. Improved system performance by freeing up the CPU for other tasks. Question. Briefly describe the steps involved in a DMA transfer. Answers. CPU initialization, DMA request, bus takeover, data transfer, and completion notification. Question. Can a DMA controller operate without any involvement from the CPU? Answers. No. The CPU initializes the DMA controller and receives notification upon completion. Hey everyone, thanks for tuning in and learning about DMA controllers. These hidden gems really help our computers run smoothly. If you found this video helpful, consider giving it a thumbs up to let me know. And if you have any questions or thoughts on DMA controllers, leave a comment below. I'd love to hear from you. For even more tech breakdowns and interesting content, hit that subscribe button and join the community.